It seems as though we must use sometimes the one theory and sometimes the other, while at times we may use either. We are faced with a new kind of difficulty. We have two contradictory pictures of reality separately. Neither of them fully explains the phenomena of light, but together they do.
As what Einstein stated, light's kind of weird. Sometimes light behaves as a wave, and other times it behaves as a particle. Um, Now, as for a certain phenomenon, yes, it could be proven using both methods, like reflection or refraction, but there are certain ideas that can only be described using just the wave theory, and there is no particle equivalent in explaining it. And yet again, there's other things, like for example, the photoelectric effect and black body emission, that can only be explained by the particle theory, and unfortunately, the wave theory will fall apart as waves are deemed to be continuous waves. Meanwhile, as you have learned before, E equals hf, that's for discrete particles, where quantum mechanics starts to come into play. So, here's another weird thing about photons. Photons, even though they don't have mass, they possess momentum. I know, pause and think about that. We know that momentum is equal to mass times velocity, and sure, light travels at the speed of 3 times 10 to the 8. But since light is massless, well, how can it have momentum? And that's rather strange. But through various experiments, it was proven that light does have momentum. After all, if you think about what's been happening with the photoelectric effect, you got a photon of light striking a surface, causing pretty much a collision where momentum must be conserved in order for the electron to become ejected. So yeah, the photon has to have momentum. As for the formula, it does boil down to this formula right here. Momentum of a photon is equal to Planck's constant divided by wavelength. How in the world do we come about this? Well, let's go back to relativity. We might remember these two equations here. For example, relativistic momentum is equal to this stuff over here, and out of sheer laziness, I'm just going to write down something for the Lorentz factor. We know it's going to be 1 minus v squared over c squared, but yeah, I'll just write it as something just to keep this nice and clean. Okay, and we also have the other formula for energy, or total energy, which is this formula right over here. Now let's say we take this formula here and we isolate for m naught. Then it would look something like that. And then with the formula above, let me just put a C here and drop all the stuff up there. You can imagine that the something upstairs divides out with the something downstairs, and you're left with this formula here. Of course, we can divide out one of the C's downstairs with the C upstairs, and keeping in mind that energy of a photon is equal to Planck's constant times frequency, we could settle with this formula here, but we can also simplify it a little bit more, since F over C is also equal to 1 over lambda. So we end up with this. Planck's constant is equal to, momentum is equal to Planck's constant divided by wavelength. And that's the derivation of the formula. With that in mind, how about we practice through this problem right over here? I'll give you guys a moment. You guys ready for the answer? Well, depending upon whether you chose Team Red or Team Green, this would have been your corresponding answers right below. Hopefully you got the answers for it. If not, check your work. Make sure you also check your units as well. Remember that nanometers means times 10 to the negative 9. Another thing that you might want to watch out for is that on your calculator, if you're using it as a reference, you might have subbed in the wrong constant. I know that constant 6 and constant 9 look pretty much the same, but if you look carefully, constant 9 has an H with a line on top. It's also known as H bar, something that you'll be using in university. After all, with regards to Planck's constant and electrons orbiting, well, electrons often have a circular orbit, hence the 2 pi. That's often factored into the calculations, and sometimes out of sheer simplicity, physicists will denote that as h bar. For us, we're only using cons 6, so please avoid using cons 9 if you want to avoid that mathematical mistake. Another proof that photons have momentum is by the use of something known as solar sails. So for example, if you have the sun, Mr. Golden Sun, he's shining the light, and if the photons have momentum on it, you'll have this action-reaction pair, where the photons, when they strike the sail will act in the opposite direction and move away from the sun. And I know this sounds all hypothetical and all, but it ain't hypothetical anymore. In fact, in Japan, they have this thing called the Icarus, or the interplanetary kite craft accelerated by radiation of the sun. And yeah, they were successful with the satellite over here that was able to orbit around Venus using this technology back in 2010. In fact, there's also a classroom demonstration called Crookes radiometer, which does effectively the same thing. So you'll notice that there's a little sail on top up here, one side coated nice and dark and the other side is exposed. And the idea is that you have a very, very bright light source shining at it. And as it shines at it, well, the light won't be absorbed by the white particle, but it'll be absorbed by the black one. And you're going to notice that there's an action-reaction pair, which causes it to rotate around. Here's a quick video of one happening in action using a laser. Woohoo, check out that thing going spin, spin, spin. You know what's another acronym? LASER, if you didn't know already. You can pause the video if you want to read the description of it. And yeah, this laser used to be in Toronto, in the Ontario Science Centre. If you've ever been to Kids Spark on, I think, the third floor down, it used to be a laser museum. I remember when I was a kid, I saw that laser, and the laser is about the width of your physics classroom. It was a huge laser, and they were able to, I think it was like a transparent balloon outside and a black balloon inside, and they were able to pop that black balloon with this awesome demonstration. Here's another proof that light also behaves as a particle. If you have this high energy radiation striking on a screen, it may cause an electron to eject. Now, it doesn't mean that all energy is lost. For whatever energy that's left over, it results in more radiation, usually that of X-ray radiation, but of a lower energy. And if you look at the picture below, I know it's a mirror image, but here's some simple calculations. For example, you have an X-ray entering it at 6 picometers in its wavelength. You'll notice that at the end, the wavelength stretches out, meaning that the energy of the photon has now decreased. So you have a loss in energy of the new photon, but not all the energy is lost, for when the electron is ejected, the measurable energy in the electron is possible. In fact, this is some sample calculations that if you want to try to do it, you can test it out yourself to see that this math does work out to that answer up there. In fact, even the angle of how it deflects can be proven by this formula right over here, but we'll save that for university. For the purposes of high school, we just need to keep this part here in mind. That photons, when they react with an electron and strike it, it behaves just like that of an elastic collision, where energy is conserved. There's an issue with regards to the planetary model of electrons. That's one where you imagine an electron just perfectly orbits around a proton. The issue with this is that, as you know, energy unfortunately gets lost, and as the energy gets lost, it's going to circle in and in and in and in, and eventually they're going to bond together, and the world as we know it will collapse. So that can't be the case. So we need another theory to describe how in the world do electrons behave, and it does behave in a rather trippy way in the world of standing waves. So before we go on to the exemplar, let's go through a little bit of grade 11 review. So in grade 11, you might have learned about standing waves in resonance columns. For example, in the closed air resonance column, where it's closed on one end and it's open on the other, you'll notice that an antinode is formed over here and a node is formed right here. And that represents a small fraction of a full wavelength. So if this is the full wavelength over here, and this is half a wavelength, you'll notice that this part over here represents a quarter of a wavelength. In fact, the next order where it's going to resonate is in this pattern here, and it can resonate again in this pattern for the same exact frequency. Or plan B, within the same length of a column, so let's say the length of the column is specifically this long, well, there's different orders of resonance that can occur inside this column. It can either resonate at its first order resonance, like so, or it can resonate at a higher frequency, or even a higher frequency. In all cases, it forms something known as a standing wave inside. In fact, sometimes we imagine that electrons may behave as a standing wave within their orbit. So if you look at these pictures over here, these are different possibilities of how electrons can behave as a standing wave. In fact, in its locations where an antinode is formed is probably the energy signature that we receive, denoting the presence of an electron.
Not just light, monsieur, but matter as well. Pardon me?
The French prince and physicist Louis de Broglie generalized Einstein's principle, applying it to the entire physical world.
Electrons, protons, photons, tout le monde. Everything has a dual nature.
De Broglie also proposed that electrons themselves exhibited wave-like behavior. These pilot waves adjust their wavelengths periodically, just enough to fit the electron into a stable orbit of a fixed radii from the nucleus.
Okay, with that in mind, which of these two configurations is correct? Is the one on the left correct, or the one on the right correct? And the correct answer is the one on the left. What's wrong with the one on the right? Well, look what's happening right over here. If that wave was to keep on going, then you have a crest interacting with a trough from the previous wave, thus netting everything to a zero. So in order for it to be a standing wave, it has to be in order where it can maintain resonance within its orbit and not interfere with the previous generated wave. So that's what suggests that, you know what, maybe it is just a probability function of an electron with, for example, these closed walls over here. It can either resonate at its first order resonance, at its second order resonance, maybe even at its third order resonance. In any case, all we're observing is effectively when the antinode is formed, and that is where the highest probability of where an electron exists. And this brings up another interesting formula. And it's taken by this previous momentum of a photon formula, where it states that, hey, if this P represents momentum, then we can technically replace that with mv right over here. And maybe if we bring the lambda on top, we got lambda is equal to h over mv. Or this formula right over here, which is often denoted as the de Broglie wavelength, which suggests that not only electrons might behave as a wave, but maybe other things in life also behave as waves too. And we'll go through two extreme examples of when this formula is practical and when this formula is probably meaningless for our calculations. Here's the first one. Let's say that we have an electron which contains 50 electron volts of kinetic energy. What is the corresponding wavelength of this electron right over here? Keeping in mind that when you do your calculations, make sure you convert EV into joules. And to convert into joules, you multiply that by 1.602 times 10 to the negative 19 joules per electron volt. So go ahead, go and calculate that out. What is the corresponding de Broglie wavelength? Ready for the answer? Well, one thing that I did actually ahead of time was that I checked to see if it was reasonable for our calculations to be kept nice and simple. And yeah, if the electron had more than 2,500 electron volts, then unfortunately it's going to start becoming relativistic and you can't use the simple formula anymore. Luckily for us, 50 electron volts is perfectly fine. All right, and to get to the answer of this, yeah, you do need to have two formulas. First off, you need the de Broglie wavelength formula, but since P is equal to mv, well, we'll see that there's a v right over here for kinetic energy. So you take the kinetic energy formula and you isolate for v, where v is equal to the root 2 ek over m, and then you sub it right into this v right over here and you work it out. If all goes well, you'll end up with an answer like this. Now, before we move forwards, I left this number over here as a reference. That is the assumed radius of an electron. Not that we're able to measure the real one, but it gives us a good reference value. All right, so you'll see the electron is at the order of 10 to the negative 15, and this wavelength is to the negative 10, meaning that this wavelength here is about 10,000 times larger than the size of what you're measuring. So you have a tiny little object, and its wavelength is significantly larger than the object itself. And this is one example where it is practical to use this formula here. Here's the other extreme.
Merida! Curse this dress! Merida, stop this! Don't you dare loose another arrow! Merida, I forbid it!
Ooh, Look at that arrow. You see it wobble back and forth? Yes, it's going to naturally wobble back and forth. After all, the arrow itself, it is a physical object. So yeah, it has a natural tendency to want to resonate at its second order open end resonance. But we're not talking about this as the wavelength. That's not the case. We're going to say that let's assume that this arrow over here is in the shape of a sphere. All right, the way how physicists like doing that. So a standard competition arrow has a mass of 80 grams, and yeah, they do typically travel at roughly the speed over here. So given this information over here, take a moment to figure out its corresponding de Broglie wavelength. And hopefully you ended up getting this as your answer. Now this is where I want to turn back to the size of an electron. As you've seen, the size of an electron is to the -15, so having an answer to the -34, wow, that's really tiny, even smaller than that of an electron. And this is a arrow which you can see in real life. So this is an example where it doesn't seem practical in using de Broglie's formula. So you really got to compare the corresponding wavelength with the object, where if the wavelength is larger than the size of the object, then it's a useful calculation, but in this case over here, it's meaningless. And yeah, you could say that this formula over here, there is an inverse correlation. So if the velocity technically is slow enough, so this number is small enough, then maybe you'll end up getting a wavelength that's comparable to the size of the object. But I don't think any of us will live that long to see that slow of an arrow moving just to calculate a corresponding wavelength. In fact, just as a fun fact, the smallest measurable size that's practical is to the -35, and that's often known as the Planck length. So in this case here, no, sorry, good game. Nice try. Suppose you have an electron, and this electron passes through a double slit opening. You'd expect that, technically speaking, the electron, if it's lucky enough, it'll pass through either the upper or lower opening, resulting in a pattern that looks something like this on the screen. However, if you give it enough time, it won't just be two groupings of electrons hitting the screen itself. You end up getting this rather distributed pattern that seems to be evenly separated. In fact, after 70,000 trials of, remember, this is one electron moving at a time, you end up getting a pattern that looks mysteriously like this. Which doesn't make any sense at all. Remember, this is one electron passing through the openings at a time. Not two, not three at once, just one at a time. So there are many interpretations of this. I strongly recommend that you read through these pages in your textbook. But as a brief synopsis, there are 4 of them to describe in the textbook itself. The first one is that of how electrons may change from a particle to a wave. So this electron, even while it's moving, it just behaves as a wave, and with that wave, you end up getting that typical double slit interference pattern. But by the time it reaches the screen, it says, I give up being a wave and I turn into a particle again. There's also this other interesting one where it states that an electron has this pilot in front of it, or a pilot wave. So it's looking ahead, seeking for its, I guess, best intentions, and as it passes through, those waves themselves result in this interference pattern, and the electron responds to that interference pattern. I'll show you a video on this momentarily. Others believe that, just like in, I guess, the Marvel comic universes and whatnot, that we live in this multiverse. So there's multiple copies of electrons in different parallel universes, and somehow they communicate with each other to agree upon what they should look like on the far side to amuse us humans. And, there's other scientists which just take the information as is and accept it as it is, and sometimes we just don't have answers. We just observe things, and these are the concluding results. Anyways, here's a brief video describing the pilot wave interpretation.
Check this out. I'm using this speaker to vibrate a petri dish containing silicon oil. Now if I take this toothpick and I make a little droplet on the surface, the droplet will stay there, hovering above the surface. The droplet is actually bouncing, and it'll keep bouncing for a very long time. Now the reason for this is there's a little layer of air between the droplet and the surface. And the droplet's bouncing so rapidly that that layer never shrinks to about 100 nanometers, which is what it would take for the droplet to recombine with the oil. Now, every time the droplet lands on the surface, it creates a wave. But this is a special type of wave, driven by the vibration of the oil bath. It is a standing wave, meaning that it's not traveling out, it's just oscillating up and down. So the droplet makes the wave, and then it interacts with that wave on its next bounce. If the drop lands on one side of the wave, it is pushed forwards. And as long as the bounce of the droplet remains synchronized with the wave, it'll keep landing on the front side of the wave and getting pushed farther forwards. Droplets like these are known as walkers. The bouncing oil drops have been known about since the 1970s, but only recently has it been discovered that you can use these little droplets to replicate many of the strange phenomena of quantum mechanics. Now, obviously, this is not a quantum system. The droplets are about a millimeter in diameter, but you can think of the droplets like quantum particles, say electrons. One experiment that captures the key features of quantum mechanics is the double slit experiment. If you send a beam of electrons at two narrow slits, well, the electrons, rather than behaving like particles and ending up in two clumps behind the slits, they produce an interference pattern, even when you send each electron through one at a time. With walking droplets, the pilot wave goes through both slits, interfering with itself, while the droplet only goes through one slit. The droplet doesn't move in a straight line, though. It's deflected by its interaction with the wave. The resulting distribution of where the droplets end up looks very similar to quantum double-slit interference patterns. Or take tunneling. In quantum mechanics, it's possible for a particle to get through a barrier that it wouldn't classically have enough energy to get over. This has been demonstrated with walkers by creating a shallow barrier under the surface of the oil. Usually the barrier reflects the pilot wave and its bouncing droplet, but in rare cases the droplet does cross the boundary. And the probability of the droplet crossing the barrier decreases exponentially with the increasing width of the barrier, just as in quantum tunneling. Perhaps the most surprising thing about these walkers is they exhibit quantization, just like electrons bound to atoms. Here the walker is confined to a circular corral. The droplet seems to move around randomly as it interacts with its pilot wave. The complex interaction between the droplet and the wave leads to chaotic motion of the droplet. But over time, a pattern builds up. This is the probability density of finding the droplet at any point within the corral, and it looks very similar to the probability density of electrons confined in a quantum corral. All of these similarities are no coincidence. The walking droplets actually create a remarkable physical realization of a theory proposed by de Broglie nearly 100 years ago in the early days of quantum mechanics. He postulated that all particles have a wave that accompanies them and guides their motion, and that wave is actually created by tiny oscillations of the particle. Now, this pilot wave theory was marginalized when the standard Copenhagen interpretation became widely adopted. The Copenhagen interpretation excludes anything that cannot be directly observed, and it says everything that can be known about a particle is contained in its so-called wave function. But adopting this view forces you to give up on some common sense notions, like the idea that particles have a definite position and momentum even when they're not being measured. And it also meant that the universe was no longer deterministic. Randomness is built into standard quantum mechanics. For example, take the double slit experiment. According to quantum mechanics, the wave function of the electron is a superposition of the electron going through one slit and the other slit simultaneously. Using this wave function, you can calculate the probability of where the electron is likely to be. And then when you detect it at the screen, the electron pops up at one point at random that was in that distribution. We say that its wave function collapses instantaneously at the moment of measurement. You can't say that the electron was there before you measured it, and you can't even say that the electron must have gone through one slit or the other. Compare that with the picture provided by the bouncing droplets. In this case, the pilot wave goes through both slits, but the droplet only goes through one. The droplet is pushed around by its interaction with the wave so that the resulting statistical distribution is the same. The droplet never exists in two places at once, and there's no randomness. If there is any uncertainty, it's just due to our ignorance of what's going on. It's not that it doesn't exist. So pilot wave dynamics can produce many of the same results as quantum mechanics. Does this mean that this is really what quantum particles are doing? No. But I think it'll at least suggest that this is possible. These are possible dynamics that could lead to the statistics which are captured in the quantum mechanical theory. And what's appealing about this is it gives you a clear idea of what's going on. You don't have to abandon the idea that the universe is deterministic, and you get particles with definite position and momenta. I think it's great that we have two competing theories for the same experiments. And they both ask you to accept odd things, just different odd things. And it comes down to what you're comfortable with, really, whether you prefer the Copenhagen interpretation of standard quantum mechanics or a pilot wave theory. Let me know what you think in the comments. Do you like the pilot waves? I mean, it's definitely a very appealing picture. Whether or not it corresponds to reality, that remains to be seen.
The uncertainty principle states that the more you know about an electron's position, the less you know about its corresponding velocity. Now remember that velocity is a part of momentum, which is mass times velocity. And it's very weird because if you try to confine an electron to a smaller space expecting to make it through that smaller opening, instead it starts to spread out a little bit. His formula, if you're curious, it looks something like this. Not that it matters too much, but if you tried to calculate it out, remember that Planck's constant is already a small enough number. So a small number divided by a number around 12, well, it makes it even a smaller number itself. So this is practical, especially if you have a very small opening. For the smaller the opening, the only for this number to be true is if this number over here grew larger.
So I've been breaking my bones for years how I could possibly show this to my students in the classroom convincingly. And the way I'm going to do that is as follows. I have here a green laser, and the green laser I'm going to shine through a slit. So this is the slit. So this is opaque, and this is opaque, and I shine the green laser through the opening, and you're going to see it right there on the screen. No problem. But of course, in this direction, this beam is a little bit restricted, so I call this delta x. In this direction, it's not restricted at all, so I don't even have to think about Heisenberg's uncertainty principle in this direction. This direction is going to become a concern. I will blow this cross-section of the light up, because now I'm going to make the slits narrower, so I'm going to put it here. So this part of the light you will not see there, and this part of the light you will not see there. And then I continue that. I make it even smaller. And so this part of the light you will not see, and this part of the light you will not see. But this delta x has become so small that Heisenberg says, you can't do that. If delta x is going to be this small, and this is the x direction, then the momentum of the light in this direction is not well known. And so if the momentum of the light in this direction is uncertain by a large amount, then the light that goes through the slit might easily spread, so it wouldn't come out right at the middle on the wall, but it may come out here, or there, or there, or there, or there. So the crazy thing is, the smaller you make the slit, the wider you're going to see the image on the screen, because of Heisenberg's uncertainty principle. The more you constrain delta x, the larger delta p will be, and delta p means that you add to the momentum of the light a component in this direction, and therefore the light will spread. Before I show you this experiment, you may want to ask yourself a reasonable question, and that is, can we apply Heisenberg's uncertainty principle to light? In other words, does light have a momentum? And now looking at John, my friend, who asked me this by email. Of course it does, because light can behave like a particle, and all particles have a momentum. But the momentum is not mv, because the mass of a light photon is 0. So now you will say, no problem. A mass is 0, the velocity is the speed of light. Well, 0 times the speed of light is still 0. However, a light photon does have momentum. And I could show you the equation. But I said to myself, why should I? Because you learn nothing. You will see just one other equation, and you have already seen so many, so you get even more confused. So it should be enough for me that you accept the fact that light does have a momentum. And if you want to know what it is, you can come to me after this lecture, and I will tell you what it is. Thus my conclusion is, yes, you can use this experiment. Light has a momentum, and therefore, what I just told you, the narrower the slit, the wider the light will spread, is going to be realistic. So, I'm going to move to the other side of the table, and I'm going to turn on the laser. Did I open it? Do I go clockwise or counterclockwise? Okay, there we go. There we go. Look at the center portion. Look that the center portion is now going out in horizontal direction. You see it's getting bigger? You're seeing it's getting bigger, it's getting wider. Heisenberg is having lots of fun now. He knows this has to happen. I'm making it smaller, and I'm making it smaller. And that center part gets bigger and bigger and bigger. Forget the dashed lines, right? It's now almost 10 centimeters. I've made some calculations, and they show that if the slit opening is 5 microns, then the central portion of the light on the wall is about 10 centimeters. So the opening must be approximately 5 microns now. And yet, what you see on the wall is about 10 centimeters, which is about 20,000 times larger than the 5 micron opening of the slit. I can even go one step further, and I'll try to go to make the slit about 1 micron. Look at that central portion. 1 micron. I calculated if it is 1 micron, that middle part should be about 25 centimeters. 50 centimeters. That's right, should be 50 centimeters. And I think I can reach that point, and you can still see it. This is about 50 centimeters. Don't accuse me that it is so faint. Can you imagine that any light goes through a slit which is 1 micron wide? That has nothing to do with Heisenberg. That's simply the fact that I don't let much light through. But you see now that that central point is now this big. It's about 50 centimeters. 50 centimeters! Only because it's being squeezed through a 1 micron opening. That is Heisenberg's uncertainty principle. An amazing and very non-intuitive consequence of quantum mechanics, because he derived his uncertainty principle from the equations of quantum mechanics.
In fact, I would recommend that if you have a chance, watch the lecture. It's about an hour long, but if you notice from up above, he was talking about the quantum nature of electrons in their excitation and emission spectrum, and he talks about it as well. So it's a great video to watch, more or less for a review for this unit, as we're almost done with this unit. In fact, in your textbook, if you flip over to page 626, it describes some properties of electrons, and it just summarizes everything we've learned so far. First, we learned that with regards to photons, sometimes photons may just experience a perfectly elastic collision with metals, resulting in a specular reflection. Sometimes the photons may eject electrons, and that's known as the photoelectric effect. Sometimes a photon interacts with matter. Not only will it eject an electron, but a photon will still emit through. Just mind you that conservation of energy must still be true. So that means that with the photon that's leaving, it should have less energy than what it started off with. And if you add up the energy of that photon plus the kinetic energy of the electron, it will equal to the original energy of the photon itself. So it's a perfectly elastic collision. for the Compton effect. Sometimes the photon may be temporarily absorbed by the electron as it's brought up to a higher energy level, and that's known as the excited state. And once that electron drops, then you have, or this is the absorption spectra, and then you have the emission. As for the last one, I've never seen pair creation, but there is such thing as pair production, where if a photon interacts with a very large nucleus, it collides with it, and then you end up having these two opposite people. You have an electron and its complete counterpart called the positron. So yeah, it'll still net to a value of 0, but it's interesting that energy and momentum is conserved in this type of collision. Before I sign off, one last thing to emphasize is that if you go to Perimeter Institute's animations, they have some awesome animations showing what you should expect when you have particles going through two openings and how electrons seem to be counterintuitive and behave more like waves. So yeah, if you have a chance, check out that. Aside from that, make sure you get through your homework and review well, and I'll catch you in the next episode. Bye for now.